Welcome back. Where I had just left off, we were trying to figure out this area between these two curves, and we figured out that it's really the area between the curves, between the points 0, x equals 0, and x equals 1. And I was proposing a way to do it. Let's figure out the entire area under the square root of x from 0 to 1, and we can subtract from that this purple area, which is the area under x squared. So just based on the last example we did, we could just write the indefinite integral, and I'm not going to rewrite the fundamental theorem from calculus because I think you know that by now. Let me do it in a loud color, magenta. So I want to know the larger area, right? The area under just the square root of x. That's kind of like the combined area. Well, that's just from 0 to 1, the integral of square root of x, right? Because square root of x is the green function, dx. And I want to subtract from that the area from 0 to 1, what's under x squared. X squared dx. And I just want to make a point. This could have just been rewritten this way. You could just rewrite a new function, which is the difference of these two functions, and it would have been equivalent. You could have said this. This isn't kind of a step of the problem, but you could have done it this way. In fact, some people start this way. Say, well, this is the same thing as the integral from 0 to 1 of square root of x minus x squared dx. So you could do it as two separate problems, two separate indefinite integrals, or you could do it as one indefinite integral. Actually, that might be even simpler because when you evaluate it from 1 to 0, it simplifies things a little bit. So let's stick with the second one. So first of all, we just have to figure out what the antiderivative of this inner expression is. So you haven't seen square root of x yet. Do you think you know how to do it? Well, I think you do. Let's say that equals square root of x is just x to the 1/2 power, right? So we just use the same antiderivative rules we've always used. We raise it one more power, so it becomes x to the 3/2, right? It was 1/2, we added 1 to it. And then we divide by this new exponent. So dividing by a fraction is like multiplying by its reciprocal, right? So it's 2/3 x to the 3/2. And then minus, I think the second term is pretty easy for you, minus 1/3 x to the 3rd, right? That's the antiderivative of minus x squared, minus 1/3 x to the 3rd. And we're going to have to evaluate this thing at 0 and 1 and subtract the difference. Subtract this expression evaluated at 0 from this expression evaluated at 1. Well, this equals, I think I'm running out of space. What happens when x equals 1? 1 to the 3/2 is 1. 1 to the 3rd is 1. So it's 2/3 minus 1/3. Well, that's easy. It's 1/3. Right? I just put 1 in for x. And then when x is equal to 0, what is this expression equal? Well, that's easy too. That's 0. So there you go. 1/3 minus 0, or 1/3. That's kind of neat. That the area between, I find this kind of exciting because you would, if I just my intuition, I was like, oh, I have these two curves, and I mean, they do intersect at a nice integral number, a nice integer number, but what? It's probably going to be some really messy number of what the area is between these two curves, right? Maybe, who knows? Maybe it'll involve some, a circle involves pi, which is this really messy number. So maybe all curves have these kind of messy areas. But this one, it's just one of those neat things about math. The area between the square root of x and x squared is 1/3, which is a pretty clean number. I think I'm gonna let it. Actually, let me do one more problem since I have time. It's a bit of a trick problem. I mean, it's not. You might actually find this easy, but let's figure out the area between f of x is equal to well, let me just, I don't know, x to the 5th. I'm going to do something simple. Let me draw it actually. Whoa, I don't know what's going on. Okay, look at that. Okay, let me draw the x-axis. Okay. And I'll draw x. Well, x to the fifth is going to go up super fast. It's going to go like that. Something like that. It's going to go up real fast. Let's say I wanted to figure out the area. It's going to, on this side, it's going to go real fast too. Between that, and instead of figuring out the area between the x-axis and that, f of x, I want to figure out the area between f of x and instead of figuring out this bottom area, right? Like the normal problems we've done, we would figure out this type of area, you know, between 2 points. Let's say I want to figure out the area inside of the curve. Where the height here is 32. So I want to figure out this area inside the curve. How do we do that? Well, one way we could do it is just like we did the last one. We can figure out some function that's essentially a line, a horizontal line that goes straight across here. And we'll essentially just be figuring out the area between the two functions. So what's a function that's a line that just goes straight at y equals 32? I think I just gave you the answer. Exactly. Let me stick it to that. Let me stick with that greenish color. So we could say g of x is equal to 32. It's just a constant function. It just goes straight across. And then we need to figure out what the area is between the two. So we need to figure out what are these 2 points. Right? So when does x to the fifth equal 32? Well, I mean, you could solve it algebraically, but I think you could say x to the fifth equals 32. X is equal to 2. And actually, you know what? I made a mistake. Let's say that this is not equal to x to the fifth. Let's say that f of x is equal to x to the absolute value of x to the fifth. Because the mistake, obviously, x to the fifth is not a parabola-looking thing. X to the fifth goes negative like this. But I have committed so much to this cup shape that I'll make it the absolute value of x to the fifth. So if I say the absolute value of x to the fifth is equal to 32, I think you see where I realized my mistake. But if I say the absolute value of x to the fifth is equal to 32, there's 2 places where that's true. It's x is equal to plus or minus 2, right? These are the 2 points. I should have done something with an even exponent so I could have had this cup shape. But anyway, the absolute value solves my problem. So what is this area? So we know it's between -2 and 2, so we just set up the indefinite integral. It's the indefinite integral from -2 to 2 of the top function, the top boundary, 32, minus the bottom boundary, minus, well, this will be a little bit tricky, but minus the absolute value of x to the fifth dx. And actually, instead of doing this, I think you could see that there's symmetry here. So we could just figure out this area and multiply by 2, right? This problem's a little hairy. This problem ended up being, just because I had a bad choice of initial function, not exactly what I wanted, but we'll work on forward. So instead of doing that, let's do the integral from 0 to 2 of 32 minus x to the fifth dx. And then multiply that by 2. So what is that? That's 32x minus x to the sixth over 6. And we're going to value it from 2 and 0. At 2, it's 64 minus 64 over 6. Right? 2 to the 6th is 64. And then at 0, 32 times 0 is 0. And then x to the 6th, that's 0. So the answer is 64 minus 64 over 6. I'm about to run out of time. That's just a fraction problem there. Oh, and that's half of it, right? So we want to multiply that by 2. So if we multiply that by 2, we get, what, 128 minus 128 over 6. I haven't figured out what it is. Well, I guess we could figure it out. It's 128 times 1 minus 1/6, or 128 times 5/6, and I don't know what that is. I can multiply it if I wanted to, but I have 10 seconds left, so I'll leave you there. Hope I didn't confuse you. See you soon.